This spring fascinates me. I'll completely uncoil it, except for a few kinks. Now, watch as I put it in hot water, 75 degrees or so. Rapidly, the spring reforms. Let's watch it again, but close up. I stretch the spring, and then, to slow down the action, use a hairdryer to heat it. This spring is made from nitinol wire. The name comes from the elements it contains and where it was discovered: nickel and titanium and the Naval Ordnance Lab. It's showing what's called the shape memory effect. A length of this wire was formed at very high temperatures into a spring. This shape setting occurs at temperatures above about 500 degrees Celsius and then cooled. Almost no matter how it's bent at room temperature, it returns to its original shape when heated at 75 degrees Celsius or so. So why does nitinol have this memory? The key is understanding how the atoms move in response to stretching and bending of a piece of nitinol. Typically, any metal, whether nitinol or not, is comprised of small grains that, depending on the material, are microns to nanometers across. And each grain is comprised of atoms arranged in a regular, repeating pattern. If this metal rod were held at the top and stretched, then the grains might elongate. They can do this because the atoms inside move a bit. In a metal, bonds can reform more easily than in nonmetals, and so the atoms slip. Although it's a bit more complicated than implied here, which looks like spherical atoms rolling along each other. It involves defects in the crystal that allow the atoms to move only small amounts. In nitinol, though, generally the atoms don't slip. They accommodate the stresses from bending, stretching, compression, and so on in a different way, which produces the memory effect. Here's a simplified two-dimensional version of the atomic structure of nitinol, but one that captures the essence of why it has a temperature-dependent memory. The crystallites in the small grains have a nice, tidy, highly symmetric arrangement. The atoms sit on the corners of squares. At temperatures above 500 degrees Celsius or so, the nitinol can be shaped into whatever form is useful. For example, the spring I showed you earlier. When it cools, the crystal structure, the arrangement of the atoms, changes only slightly. Notice that it's very similar. All the atoms are connected in the same way, but the nice, tidy squares are now rhombuses. Notice that even though the atoms move a bit, the overall shape doesn't really change. So, for example, if you fashioned a spring, it still looks like a spring. This doesn't seem very exciting, but this structure has a unique property. It's composed of rhombuses that are mirror images. For example, notice the position of the atoms above and below this line aren't identical, but are reflections of each other. This is called a twin structure. You could have all of the rhombuses oriented this way or this way. And as you can now see, when the nitinol cools, it forms equal amounts of these two orientations of rhombuses. One's oriented this way and one's this way. What produces the memory effect in nitinol is that these two orientations can easily be changed from one to the other with very small motions of the atoms. For example, if I take the cooled nitinol and change its shape, some of the crystallites might experience a shear, a force across the top. Notice that in response, the atoms move and change the ratio of the two types of rhombuses. In this example, they all change to one type. You could imagine that in response to different forces, that in a large enough crystal, there would be hundreds of mixtures of these two rhombuses, and many, many more in a three-dimensional structure. But notice this. At all times, the atoms are connected in the same way as in the high-temperature phase, unlike in slip, where atoms can rearrange quite a bit more. So when the temperature is raised again, these rhombuses, no matter how they are distributed, return to tidy squares. The only structure that can result is the original structure, and so the nitinol reverts to the shape it had at high temperature. There are some clever uses for nitinol. For example, this device has fascinated me since childhood. It's a type of engine. Its construction is very simple, a large and small wheel, each grooved on their side, with a loop of nitinol wire that runs through the grooves and connects them. To make it run, I just contact the lower edge of the small bottom wheel with water, which I've heated again to 75 degrees Celsius. Then spin the top wheel a bit, and the device then runs on its own. It uses the temperature difference between the water and the air to power the engine. When I remove the water, the wheel stops spinning. This engine runs because this loop of nitinol wire was originally straight at a very high temperature, so as it's heated, it tries to straighten. To see how that causes the engine to operate, watch what happens as I contact the lower wheel with the heated water. I'll mark the position of the wire on the left with a yellow line. Then, when I start the wheel, the wire's distance from the initial position is much greater. It's hard to see, so I'll mark its position with a purple line. This happens because when the bottom wheel comes into contact with the hot water, the section of the wire highlighted here in orange is heated. If it were not in a loop, then the wire would be straight like this. But because it's in a loop, as it tries to straighten, it exerts a force on the wheel, which causes it to turn. Let's break this down. On the right, the air-cooled wire returns. It wraps onto the wheel. As the water heats the wire, it starts to straighten, but is restrained by being in a loop. This creates a force at this point on the wheel from this fulcrum, which is the last point of contact of the wire on the wheel. This generates a force about the center of the wheel, which is transmitted as torque and sets in motion the engine. Although a lot of nitinol-based engines were patented, often the practical uses of nitinol are not as a shape memory metal, but as a superelastic material. Let me show you. Compare nitinol wire to a piece of copper wire. If I move the copper wire a bit and let it go, it returns to its original position. That's an elastic deformation. But if I go too far, it doesn't return to its original shape. That's plastic deformation. Compare that to this piece of nitinol wire. It shows that elastic response for small deviations, but if I do that same extreme deformation and then let go, the wire returns to its original state, even oscillating for a while. If I bend the wire into multiple loops and then release it, it becomes straight. This superelasticity is closely related to the shape memory effect. Let's compare the two phenomena and look at what's happening at the atomic level. I start with shape memory. Here's a piece of nitinol wire that's been conditioned at 500 degrees Celsius or so to be straight. At that very high temperature, the crystal structure in the grains is those tidy, neat squares. As it's cooled to room temperature, the twin structure forms, the one with the equal number of left and right rhombuses, which you recall doesn't change the overall shape much. Then, when I deform the wire, the atoms in the crystallite shift in the grains to some unequal mixture of left and right rhombuses. There are hundreds of possibilities. When I heat it with a hairdryer, the tidy, neat squares return, and the wire becomes straight again. And then as it returns to room temperature, the twin structure returns, the one with an equal number of both rhombuses. Now, let's look at a nitinol wire that showed superelasticity. It's been conditioned so that its crystal structure is those tidy, neat squares at room temperature. They would form the twin structure at minus 15 degrees Celsius, so a much lower temperature than the shape memory effect. When I apply an external force to the wire, the crystallites and the grains deform into the rhombuses, whatever mix of those would allow it to accommodate the reshaping. When I remove the force, then, because it's at room temperature, it returns to the tidy squares. Here's an example of a commercial device that uses superelastic nitinol. It's a cage-like metal tube called a stent that's used by a cardiologist. The doctor inserts it into a vessel or duct, here it's shown in a coronary artery, and it holds the walls in place. Because these are superelastic, watch this. I can severely deform it, and when I release it, it returns to its original shape. To use it, a cardiologist chooses a stent with a slightly larger diameter than the vessel wall. It's then crimped to a size smaller than the vessel, inserted, and allowed to expand. Because it's larger than the vessel's diameter, it keeps a force on the wall and resists compression. Nitinol's other commercial uses are in high-end products. Premium eyeglasses built from superelastic nitinol so they can be bent and twisted yet return to their original shape. And it's used in designs where reducing weight is critical. For example, in the 2014 Chevrolet Corvette, a nitinol device replaced a heavy motorized actuator to open and close a vent in the car's trunk. There are thousands of more uses for nitinol, and perhaps for other shape memory materials. For example, polymers that exhibit this phenomena are now in development. I'm Bill Hammack, the Engineer Guy.